and then we have 4y equal to 0. So you see that y equal to 0 is the only solution of the second equation, and the third equation gives us 1/2 for x. So the only point that we get as a critical point is actually 1/2 0. Does this point belong to the disk? Yes, because the sum of the square of its coordinates is less or equal than 0. So yeah, so we can, what's the value of the function at 1/2 0? Well, you see that here it's negative, it's minus 1/4. Okay, what about the, so now this is the only critical point, and we have to investigate the boundary. So the boundary is of course this, so we have to study the restriction to the boundary of our function. Let's see. F restricted to the boundary of the disk. Let me see, what was the function again? Okay, so this boundary can be written as y minus y squared is equal to this. So the function was x squared plus 2y squared minus x. You can write like this. So y squared plus y squared minus x. This is now equal to 1 because we are on the boundary, and this y is equal to something. We have 1 plus 1 minus x squared minus x. So we get a second order function in one variable, right? And this is something that we might call, for example, g of x, because it's a one variable function. Okay, so we need to study this g of x, and now x will be, I guess, x belonging to minus 1, 1. So you do, if you want, you do the derivative of g, and you get that this is equal to minus 2x minus 1. And if you set it equal to 0, g prime of x equal to 0 implies that minus 2x minus 1 is equal to 0, and x is equal to minus 1/2. This will be the global minimum, of course, the global maximum, sorry, because this is a quadratic thing, is something like this with a minus in front. So, all right, so then we have to see what's the coordinate for y. So y squared is equal to 1 minus x squared implies that it must be equal to this 3 divided by 4. Y is equal to plus or minus the square root of 3 divided by 2. So we have 2 points on the boundary. 2 points on the boundary. Minus 1/2, and this is plus or minus this square root of 2. And if we compute, I mean, this they will give the same function value. So if we compute the f at these points, we do get, what was the function? Okay, so it was, right, so we have 1 divided by 4 plus 2 times 3 divided by 4 minus minus plus 1/2. So we get, this is 2, this is 1. We get 2 plus 1/4, that's going to be 9 divided by 4. Is this correct? Yeah. So it looks like that. So it looks like that the max max attained at the point at the point minus 1/2 plus or minus this, and the mean is attained at this point. Yes. Let me see if I yes. Do you have any questions on this problem? Maybe I wrote it wrongly. Yeah, it's 1/2. Okay. Exercise number 2. Not 3, 2. So in exercise number 2, we want to prove that the equation e to the z minus 1 plus 2zy plus x minus 3y to the power of 3 equal to 0 defines z as C1 smooth function of x and y in a neighborhood of the point p equal to 0, 1, 1. And then we want to determine the partial derivatives. Determine the partial derivatives partial derivative with respect to x at the point 0, 1 and with respect to y2. So this is the exercise number 2. Okay. Right. So we have to use the implicit function theorem, of course. That's an application of the implicit function theorem. Let me call this thing f of x, y, z. So first of all, let's compute the partial derivative with respect to z of f at the point P. This is equal to e to the z minus 1, and then you have plus 2y, and the rest is, and then this has to be calculated at 0, 1, 1. So we do get 1 plus 2, which is different from 0. And this implies then that by implicit function theorem, f implicitly defines a function z. Okay, so this is already the first point. We want to compute the partial derivatives of z with respect to x and y at the point 0, 1 given. So let's see. We can differentiate f, for instance, with respect to x, and we do get Now we have to regard z as a function of x and y because we know that this implicit function does exist. So we get that e to the power of z minus 1, and then we multiply by the partial derivative of z with respect to x. And same thing here. We have 2y times partial derivative with respect to x of z. And we have plus 1 because we are differentiating with respect to x. And then we have this is equal to 0 because the function f of x, y, z is constantly equal to 0. Okay, so if we write, we can reshuffle, reorder these things. We get that this times e to the z minus 1 plus 2, this is equal to minus 1, which implies, oops, minus 1, which implies that this is equal to minus 1 divided by e to the z minus 1 plus 2z, right? So at the point given, so z at 0, 1, that's going to be equal to minus 1 divided by 3, right? Same thing for uh, the partial derivative with respect to y. We get e to the z minus 1 times this plus now we have to do the product rule here, 2y times dz dy plus 2z minus 9 y to the power of 2. Why is this? Yes, that's correct. This is equal to 0. And we have that the partial derivative of z with respect to y is locally equal to 9y squared minus 2z divided by 2y plus e to the z minus 1. And at the point 0, 1, actually, we know that at the point 0, 1, our implicit function z is equal to 1, so we have a value for z2. So at, at this point, we have that z of this is equal to 9 minus 2 divided by 2 plus 1, right? And this is 7 divided by 3. So that's the value of the partial derivative with respect to y of z at the point given. Any questions on this?
How did you determine that z equals 1?
Well, I mean, the point that we started with was the point 0, 1, 1, right? This point P has to fulfill f of P equal to 0. So the value of Z must be equal to 1. That's the value, right? So I mean, when you look for when you um, when you prove that that this function f defines implicitly a function z, you are also implicitly saying that this z function must fulfill the condition z of 0, 1 equal to 1 because this is how we, I mean, this is how we want it, right?
Yeah, it makes sense.
Yeah. Okay. I mean, in the end, I think that uh, I'm wondering if this, in this case, we can say that the function is unique, but I, it's probably up to an additive constant, I think. So that's our choice. Okay. Other questions? Okay, if no questions, I am going to the number 3. Number 3, we have to calculate a couple of integrals. Um, so calculate the following integrals. So the first integral to be calculated is I1, and it's equal to the double integral over some domain d1 of the function 2x divided by x squared plus y in the x dy, where d1 is equal, it's okay, so d1 is the domain bounded by the curves x equal to 0, x equal to 1, y equal to 0, and y equal to 4 minus x squared, right? So as I told you already, it's a good idea to make a little sketch of your domain. So here you have a straight line x equal to 1, and then you have x equal to 0, then you have y equal to 0, and then you have some parabola that has the maximum at x equal to 0, which is here. So it's equal to 4. So you have this. This is the parabola, and this is our domain D1, right? Rather easy to describe. Okay, then what we have to do is calculate this integral. So let's see. So x will be a free variable between 0 and 1, and y will be between 0 and 4 minus x squared in dy. We integrate in y and then in x. So what do we get? Okay, so right. So if we of okay, so 2 times x times the logarithm of x squared plus y between 4 minus x squared and 0, and that's going to be in dx. Okay, so this is equal, if you do the substitution, you get 2x logarithm of 4 minus 2x logarithm x squared in dx. What is this equal? We have logarithm of 4 times x squared between 1 and 0 minus, and that's clear. Let's see. Yes, so this has to be integrated by parts, I think. So this is equal to minus, and I open some bracket here, x squared logarithm of x squared minus the integral between 0 and 1. I differentiate logarithm now, and I get x squared times 1 divided by x squared times the derivative of what's inside, which is 2x in dx. So this is simplified, right? So we get logarithm of 4 minus, and this is also between 0 and 1. That's gonna be 0, the first one, and the second one is minus x squared between 1 and 0. So logarithm of 4 plus 1. Okay. The second integral to be calculated is a triple integral, I2. So this is equal to this, and where d2 is equal to the domain given by this set of inequalities. We have x, y, and x and y positive. We are within a disk, and z has to be greater or equal than 0 and less or equal than y. Yes, I have, but this is going to be 0 anyway. I mean, this 0 is going to be. I mean, you're doing the logarithm of x squared. This is a generalized integral, right? Between 1 and epsilon, and then you take the limit. So you get that this is equal to 0 minus epsilon squared times log of epsilon squared. And then you take the limit for epsilon that goes to 0 of this thing, and this is equal to 0. So of course you have, but it's a generalized integral, and there is a limit process implicitly done here. Okay, maybe it's a bit messy here. Let me do one thing. I cut this guy. Okay, what about the second one? Well, okay, so z is between 0 and the square root of y. And then we have essentially, at least in the xy plane, we have a disk, but we are taking only positive x and y. So we are taking this. So here there is a disk, but also x positive and y positive. And this is z to the power of 3 in dz, dx dy. Okay, so if you do the integration in z, you get 1 divided by 4 times integral in the domain, the real domain of y squared in dx dy, right? So now I guess that if you use the polar coordinates, we get that we have this is equal to 1 divided by 4 times double integral theta between 0 and pi divided by 2, r between 0 and 1. And then we have r squared sine squared theta times r, which is the Jacobian in d theta dr. And this is equal to, okay, so we have r to the power of 3, r to the power of 4. Oops. 1 divided by 16. And we have the integral between 0 and pi divided by 2 of sine square theta d theta. And this is again something that you can do with the double angle formula. Pi divided by 2, that's 1 minus cosine 2 theta divided by 2 in d theta. And this is equal to pi divided by 64. Right? Because we just split it, and then you get minus 1 divided by 16 times sine of 2 theta divided by 4 between pi divided by 2 and 0. And this is equal to pi divided by 64. Yes. Yeah, well, no, I mean, you have to show it, of course. I didn't. That was I omitted this step, but that's correct. I mean, you have to treat this integral as a generalized one. So the logarithm is not defined at zero. But of course, it is defined as a, as a limit process here, as I showed. It's the same thing that you do when you do, yeah, I mean, this is a one variable integral. Um, so the correct way to do that is with these additional details that I have added here. Of course, the result doesn't change. All right, so questions about this one or this exercise number 3? No questions? Okay. Um, all right, so if there are no questions, I can do the number 4. And then maybe after the number 4, we take a break. In the number 4, we have an integral function here. Define f of x to be equal to the integral between 0 and x of e to the power of y minus x cosine of y squared in dy. And we want to prove that u equal to f solves the initial value problem um, mm, the initial value problem. I should have rewritten everything. Okay, so prove that u equal to f solves the initial value problem u prime of x plus u of x equal to cosine x of x squared with u of 0 equal to 0, right? So we have to verify that this integral function, yes, so I mean, yeah. Okay, so I guess that this, we can write this f of x y, or f of x as 1 divided by e to the x, or e to the minus x times, it doesn't depend on the integration in the integration variable in dy. So first of all, you notice that f of 0 is equal to 0. So the boundary condition is fulfilled, is satisfied. Now we want to compute the derivative of this function f of x. We have to apply the product rule here because this is a product of two functions. So in the first, we get minus e to the minus x times f of x, no, times, sorry, times integral of this cosine of this in dy, and this is literally equal to minus, but that's not enough, sorry. this first part is equal to minus f of x. And then we have to differentiate the second one. Then we use the fundamental theorem of calculus, and we get that um, this is e to the minus x times e to the x cosine of x squared. This is what the fundamental theorem of calculus is telling you, right? So this is equal then to minus f of x plus cosine square of x squared. So if you reshuffle, if you dump the f of x on the other side, you get. So yes, this is the solution of the initial value problem. So that maybe I could call star. So the conclusion is f solves star. Questions about this?
Yes, Daniele, how did you use the boundary condition to prove that we can use the fundamental theorem of calculus?
Uh, no, I didn't use the boundary conditions to prove that. I have just used the fundamental theorem of calculus when I wanted to differentiate this function here, right? So the fundamental theorem of calculus tells you that this is equal to e of x cosine of x squared, right?
Yeah.
Do you agree?
Yeah, do we need to prove something before we can find the derivative of f of x?
No, in this case we don't, because this is, I think this exercise was an exercise uh, on derivative under the integral sign, but it was camouflaged actually. I mean, you see that there is no dependence on x in the integrand function. There is only x here. And if the x is only on the, I mean, this function is continuous and everything, you can apply fundamental theorem of calculus without problem. So you differentiated this as an integral function. So the function you have here is x that goes into the integral between 0 and x of this thing here. But the thing here does not depend on x at all. So we are fine.
Okay, thanks.
You're welcome. Okay, I think that we can stop here. We have like 3 minutes, so we can take 15 minutes break and then we conclude this exam. We solve exercise number 5 and 6 after the break. Yes. Okay, so what about we finish this? And we do the number 5 and 6. Okay, so let's solve the last two problems in this exam. We have the exercise 5. Okay, so what is this? We have, so we want to transform the differential equation y times u of x prime of xy equal to, no, minus x times u prime with respect to y equals to ux y by introducing new variables. Uh, the variables are x squared plus y squared equal to s and t equal to e to the minus x squared divided by 2. And then we want to determine a general solution to this differential equation. Determine the general solution. Okay, let's see, what did I do? All right, so if you differentiate s and t with respect to x and y, so you get that dt is equal to minus x e to the minus x squared divided by 2, and dt dy is equal to 0. So you can actually um, rewrite this one that I call star. We rewrite star um, so you write so using the chain rule. So in particular, we will have du dx, which is one of the two derivatives involved. This will be du ds times ds dx plus du dt times dt dx, etc. Right? So I go directly to write star in the new form, and this is equal to y times du ds, and then I have to write a ds dx, which is something that I computed already, which is 2x plus du dt times minus x e to the this, right? And then we have minus x times du ds times 2y, right? And then the second component doesn't exist because dt dy is equal to 0. And then this is equal to xy u. So now you see that um, you see that this guy simplifies with this guy, right? Because we have minus x2 and we have the same thing, and then what we are left with is the t du times this. There is a minus half is equal to this. All right, and uh, yeah, there is a y also in front here. Okay, let me rewrite. So I have minus xy times d u dt times e to the minus this, right? So now if x and y are different from 0, I can just divide, and I get this equal to u. Let's say that we are interested in positive x and y. So x, y, non-zero. And this is, there was a minus that I forgot. There is still a minus, and this is t, right? By definition. So we have a new differential equation. Du dt times t is equal to u. And this is what we need to solve. You can rewrite this if you want as du dt times 1 divided by u. This is equal to 1 divided by t with a minus. And if we integrate, so integrating in t both sides, we get the logarithm of u is equal to minus the logarithm of t plus some constant c. Um, yes, and this means that u of ts is equal, this constant t will likely depend on s. Um, so this is equal to some other constant k of s if I take the exponential both sides, times t if you want. This constant, I mean, we don't care about the signs, so this can be embedded into k of s. Um, yeah, so this is the final form of our solution. That's a function of s times t. Right. Yeah, it's just algebraic manipulation here. I haven't done anything especially deep. Do you have questions on this? No questions? No anything? Okay. Yeah, I don't know what's the smoothness. You can, I mean, it has to be at least a C1, I guess. But I mean, we are solving this exercise in the regime in which we can solve it. I mean, when we started from star, we already had that u prime. I mean, it's implicitly assumed that we can differentiate, otherwise this doesn't make sense. So I guess that uh, you might assume that k is c1 or whatever. this differential equation has infinitely many solutions. So the regularity here is not really the issue. Smooth enough. Nice. No worries. Okay, so the last one is again a minimization problem, I think. We want to find compute as a function of R the maximum of the function, okay, of the closed disk. Okay, so we have compute as function of R max and min of f of xy defined by 3x plus 4y, and then we have this divided by 2 over the disk, and the radius here is just called r squared. Can we use the implicit function theorem to show that the exercise implicitly gives us that we can differentiate? But this in this case, let me think. Not really. First of all, because I mean, there is nothing implicit here in this star. Everything is explicit. I don't want to find x or y. I want to find u. I don't know what you mean exactly, but implicit function theorem is also something that holds locally, okay, close to a point. Here we have a relation that should be true for a lot of points, possibly a whole subspace or subset of R2. In the case I was divided by x and y, so there, I guess that this relation holds at least for R2 less than the origin. So I don't think this can be done, and I don't see how, at least. Okay, I'll go ahead. If you want to write something else, I'll read it later. Um, so we have this function, and we want to find max and mean. And this max and mean, of course, in some sense, will depend on R because R is not fixed. So, and as usual, this function is smooth. We don't have singular points. It doesn't blow up anywhere. So we need to seek for critical points, and then we have to investigate what happens at the boundary. So the critical points of this function are as usual found by solving this nonlinear system of equation. And if you do the math, you get that this is equal to 3 minus this minus 4x equal to 0, and then you have another exponential here, 4 minus this. So we want to solve this, and we get a bunch of um, of points here. Let's see, 1 and 2. So one can divide by the exponential. That's always positive. We don't care. Strictly positive, actually. This system, I go to the other page. This system can be rewritten as 3 minus x times 3x plus 4y equal to 0, and 4 minus y times 3x plus 4y equal to 0. You recognize this 3x plus 4y that is in the function itself. And then you write that 3x plus 4y is equal to 3 divided by x, and 3x plus 4y is equal to 4 divided by y. So since these are identical things, you get 3 divided by, this is x, divided by x is equal to 4 divided by y, which implies that 3y has to be equal to 4x. Of course, I am excluding um, x different from 0, y different from 0. You can immediately see that x equal to 0 and y equal to 0 is not a point. Is not a critical point. Just substitute and you see that it doesn't solve the gradient equations. Okay, so here we have a relation between x and y, a linear one. So y is equal to 4 divided by 3 times x. And we can use it to substitute into the first equation, for instance. So we use y equal to 4 divided by 3 into 1. Remember that 1 was this equation, actually without the exponential. Um, without the exp. And what do we get? If you substitute, you get essentially something, an equation of second degree in x that can be easily solved, and you get that x is equal to plus or minus 3 divided by 5, and as a consequence y is equal to plus or minus 4 divided by 5, right? So we found two critical points, that they are 3 divided by 5 and 4 divided by 5, um, minus 3 divided by 5 and minus 4 divided by 5. Right. Okay. So I guess that, what was the function? Okay. Yes, so the point is if the radius is strictly greater than 1, so if our disk has a radius strictly greater than 1, we are in the situation in which the 2 points actually belong to the interior of the disk. So they are here and here. So if r is strictly greater than 1, we have that the max of f is equal to f computed at 3 divided by 5 and 4 divided by 5, which is equal to 5 this, and the mean of f is equal to f computed at the other point, right? Which is minus that value. Um, right. The question is now, why didn't I check the boundary in this case? Well, um, because Uh, because I guess that after this point the function does it actually peaks and then it goes down because I am increasing the radius and I mean these points belong actually to the boundary of the unit disk because the sum of the squares, so 9 divided by 25 plus 14 divided by 25 is equal to 1. So I am there. Now the question is, if I study the boundary, I do get something meaningful. Yeah, I guess that if you study the boundary, you get I mean, if R, so about the boundary, the function becomes f of xy equal to 4y plus 3x equal to e to the minus r squared divided by 2. Now r is fixed, it's just some parameter. You can parameterize the boundary using the polar coordinates. So this is actually equal to 4 r, which is now fixed, sine theta plus 3 cosine theta r e to the this. R is fixed. So the function in one variable is not in two variables, is equal to r e to the minus r squared theta, and this is some number that is fixed because we are on the boundary. And then we have a function for sine theta plus 3 cosine theta. And now you have to maximize essentially or minimize this expression in theta, and you will get the same straight line essentially, but this number now is bigger because you are on the boundary, so the values will be lower or or greater if we are talking about the mean. So the exercise here maximize, try to compute max and mean of the function for sine theta plus 3 cosine theta belonging to 0 to pi, and conclude. Yes, so this was the case for r strictly equal to 1. What happens for r less or equal than 1? So for r less or equal than 1, the CP that we found are not interior points anymore, right? Because they lie on. So um, so you get again the same problem as before. You have So we don't have any critical points, so the only thing which is left to be studied is the boundary, right? So in particular, there are no critical points belonging to the disk when, let me see, let me write, when, ah, when r is less or equal than 1. What about the boundary? Well, we are again in the same situation as before here when I, so the function at the boundary, f at the boundary of the disk is equal to essentially to r e this constant term, and then you have 4 sine theta plus 3 cosine theta. And then you have to maximize this function in theta. And yes, so you should get again, if you call this function phi of theta, and you take the first derivative, that's equal to minus 3 sine theta plus 4 cosine theta, and you set it equal to 0, you get that sine theta is equal to 4 divided by 3 cosine theta, and this happens when sine of theta is equal to 4 divided by 5, cosine theta is equal to 3 divided by 5. I think also minus is possible, or sine theta equal to minus this, cosine theta is equal to minus this. Yeah, and then you compute the value, and then you compute the points, and these are the, one will be the max and the other will be the mean. Okay, so I guess that that was the last problem. It's a bit slightly more involved because you have this um, this theta thing, no, this r that was like a parameter of the problem, but yeah. Well, that is all for today. So I guess that if you have questions, I can stay here a bit longer. Otherwise, I'll see you on Friday. Yes. So we have two seminars left according to this schedule. There is one on Friday, 23rd. Yes, and there is one on Thursday, 29. That's strange. Well, there is at least one seminar, which is on Friday. We will solve another old exam. And then there is maybe one more the day before the examination. At least I'm not sure. I will check with Marcus. So if you don't have questions, on the 29th, there is not. So what Marcus wrote here is available for general questions 8:15 to 9 only. So it's gonna be there for answering questions, and the seminar will be solving an old exam. Yes, the 29th, if this is correct, if this schedule is correct. So for sure we will solve an old exam. Ah, you already did that exam. Nice. Well, then I don't know. Uh, this is going to be changed. I will speak with Marcus. So yes, yes, I saw that. I will speak with Marcus. We can pick another one, I guess. It doesn't really matter what we do. The important thing is that you try yourself, so in advance, because this is pointless otherwise. Okay, so if you don't have any other questions, I'm gonna close this meeting.